Okay, so to get your data, hopefully you could kind of follow the diagram. The diagrams, they kind of indicate how you are calculating the number of new infections at each round. So this one goes with that, this one goes with that, and this one goes with that. Just a visual to go with how those infections are increasing. So the diagrams really just show infection round 0, you get one infected person, and then the next infection round, which would mean the infections passed on by those newly infected people. And so you can see the first one person produces 2 new infections. Those 2 each produce 2 more, so you get 4 and so on. Now, COVID would probably be somewhere in between, from what I've seen, somewhere in between this one and this one. So it's somewhere in there in the way that it spreads. And the one that's over there on the higher end might be something like smallpox or something that's even more infectious. Or you could think of this one over here on the far right. This could maybe be the spread of COVID-19 in areas that aren't using any kind of social distancing. Or for example, if we quit social distancing too quickly, it could start, the rate at which it's increasing could change. But anyways, as you complete your data table, I actually put mine into Desmos. Notice I put Desmos is okay. It's okay if you want to save a little time on this because these are condensed units. But in Desmos, the 3 rounds would look like this. So you can see I've got my data table over to the left, and then your graph should look something like this. And so the one where it's just doubling at each round, those are the green dots along the bottom, slowly increasing in steepness. And then the one that's tripling at each round, and the one that's going up by a multiple of 5 at each round, you can see is going up much more steeply. So you can see if you look at just round 4 right here, you can see the huge difference in changing that multiplier, especially as it goes down the road. First couple of rounds, you don't notice as big of a difference. But if you look down here, when you get down to round 4, the difference is sort of a handful of people versus quite a few people versus hundreds of people if that multiplier increases. So as we talk about social distancing and all the other things that we're trying to do to slow this down and get it under control, we're trying to push the multiplier down as much as we possibly can. That's what they mean by flattening the curve in a modeling type of ways, changing the multiplier. Oops. So going back here, I just want to talk a little bit about the reflections too. We looked at the data pattern, where those are coming from, and what the graphs look like. I wanted to talk about the equations. And so this is not going to be like y equals mx plus b. What I wanted to point out is that at each round in your data table, you can kind of think of it like this. At each round in your data table, like this here, you're doing 1 times 2 0 times, 1 times 2 once. This is 1 times 2 times 2. And this would, 1 times 2 times 2. This would be 1 times 2 times 2 times 2, which equals 8. And this would be starting with 1 person, 1 times 2 times 2 times 2 times 2, which is 16. So notice this right here, this is 2 squared, 2 to the third, 2 times 2 times 2 times 2 is 2 to the fourth. And the same thing is happening here. This is actually, so you got 3 to the first power. This is going to be 3 to the second power, which is 9, 3 to the third power, which is 27, and so on. 5 to the first power is 5, 5 to the second power is 25. So I'm showing how we're getting that because that helps you write your equation. So the general form for an exponential equation is y equals a times b to the power of x. So x is actually your exponent, which when I was first learning about these, I thought that was really weird. I never thought of x, the independent variable, as being the exponent. On this one, this is actually your y-intercept. Y intercept. And when we talk about exponent rules in a couple of weeks, it'll make more sense why that number is the y-intercept. But for right now, that's our y-intercept for our simulation or our scenario. That's your starting number infected. And then this number is your multiplier. So notice the first round you were going 2 times 2 times 2, and the second one you were doing 3 times 3 times 3, and the third one you were doing 5 times 5 times 5. So this thing here is your multiplier. Sometimes they call that a growth factor. And then x is your independent variable. In this case, it's the number of infection rounds, sort of like generations of infection. So for each of these, they each have a different multiplier. So the first one, where you're doing 2 times 2 times 2 times 2, it's 1 times 2 to the power of x. Second one, it's 1 times 3 to the power of x. The third one, it's 1 times 5 to the power of x. Where x is the number of infection rounds. 1 is the number of infected people at the beginning. And the 2, the 3, or the 5, that is like think of that, going back to this, that's like that, they call it R naught. That's the basic reproduction number, reproduction rate. And again, that's different for different infectious diseases, and it's also affected by societal and cultural things, like access to health care, the presence of a vaccine or a treatment, testing and stuff like that, so that people know that they have it and can stay separated. All of those things affect that, as well as the biology of the infectious disease itself and how long it can live on a surface and how it can live in the air, if it has to be in a droplet of liquid like COVID-19, or if it can just be floating as an airborne particle like measles or chickenpox. Okay, back to our math. Okay, so those are your equations for those. And so now you could predict how many people would be infected at any round by substituting that number in for X. So if you wanted to figure out how many infections you're going to have at the 10th round for each of those, you could put 10 in for X, put that into your calculator. And so we can project this into the future now and figure out how many people or how many rounds it would take for it to infect the entire city and get 80,000 people, the entire state, which is 7 million, the entire world, which is 7 billion. The thing is, we don't have a way of working backwards. So it'd be really cool if we did, well, I should say we don't have a way of working backwards with the math that we have in Algebra 1. And so it'd be really cool because like in slope-intercept form, you can choose a number for y and solve backwards for x. We can't do that for this. So you want to figure out 3 to what power equals 80,000. 2 to what power equals 80,000. 5 to what power equals 80,000, and so on. And the same for 7 million, and for one of them, 7 billion. So the way you actually have to do this is a bit of trial and error. So you actually have to get your calculator out and go, okay, I'm going to go 2 times 2 times 2 times 2, and just keep track. Like there's my fourth round right there, to the fourth power. And just keep track of how many times you do that before you hit 80,000 and so on. It seems really tedious, but what you're actually going to find is that it actually doesn't take that long. It's surprising how quickly exponential change accelerates, and so you'll find it doesn't take that long. Now, if you wanted to jump ahead, you can, especially for like, going up to billions and millions. If you wanted to jump ahead, you could say, well, I want to start off maybe going 2 to the power of, notice what I'm doing on the calculator, to the power of 10. So I'm going to start at the 10th round. And then, oh, well, that's not that close. I could try 2 to the power of 15. Okay, so now, actually, just a couple more rounds, you would be at 80,000. So you can use this to kind of jump around and hone in instead of having to start at round 1, 2, 3, 4, especially when you're trying to get up to 7 billion. on those blanks.